solution from Team Danube for this competition, LLM prompt recovery. We'll quickly introduce ourselves. So I'm Eugen. I work as a data scientist at H2.ai, and it is similar-ish like for all our team members. And yeah, I have quite some experience in Kaggle, and I'm based in Czech Republic, in Prague. Yeah, the next one is Pascal. Pascal.
Yeah, hi. So I'm also working at H2.ai as a senior principal data scientist, and I have a PhD in electrical engineering. So I then switched to machine learning, and yeah, by now also have quite some experience on Kaggle, and recently reached rank 4 on the competitions. So always happy to Kaggle.
And Philip.
Yes, hello, I'm Philip, also known as Psy or Psy on Kaggle. I also work surprisingly at H2.ai. So yeah, we collaborate also a lot during work and also quite a few times on Kaggle. I also have a PhD in computer science. I'm from Austria. I currently also live in Austria. Then did a postdoc and also have now already quite a bit of experience in industry. And yeah, for 4 years working at H2.ai. I have been multiple times rank 1 on the competition leaderboard. Currently I'm rank 3. Have been Kaggling for many years and have been touching a lot of different topics. So yeah, I don't have kind of like a favorite topic. I like to do computer vision. Many years ago, also more tabular data, but as many others, very recently, a lot of NLP, which also this competition was about. Yeah, so I will start. So we will switch throughout the presentation. I will start with the first part of our talk. So in the end, we are starting here with a little bit of an overwhelming image maybe of our solution. But what we want to do throughout the next 10, 15 minutes is to go step by step through our solution and unfold basically this summary. So as in many other data science and machine learning and Kaggle solutions and projects, many different puzzle pieces come together in order to produce the final result. So just to summarize for everyone again, the task of this competition was you are given an input text, an output text, and your task was to actually predict the thing in the middle that was given to an LLM to produce the output text, a prompt that was given with the input text to produce the output text. As these are decoder models, we cannot just go back. So we need to find some way of actually predicting the prompt. The choice of this competition was that T5 metric is used. So the prompt is encoded into an embedding vector with T5 base, and then a cosine similarity versus the target prompt was calculated, and that is the score. And that is actually very important because a lot of things in many solutions evolve around this metric optimization and finding a good way to optimize for this metric. Yeah, we can go to the next slide, Johan. Thank you. So yeah, as I already said, embedding of prediction matched versus ground truth with cosine similarity. In the beginning of the competition, so there is, I would say, always a kind of meta level in a competition, what is currently discussed, what is currently the state of the solutions. And usually in the beginning, very simple baseline solutions come up, and usually they get kind of overwhelmed with more proper modeling very quickly. But in this competition, it was a little bit different, that a very simple, let's say simple, baseline solution with like finding a good average prompt scored for long times very highly, because that's how the metric works. In the cosine space, if you have a good average prompt, that you can encode to an embedding vector, you will get a decent or actually pretty good similarity versus the things that evolve around this average prompt. So let's say a simple constant solution, just saying like improve the following text, would already score 0.59 on the leaderboard. And actually the highest score in the end was in the range of 0.71. So yeah, this is already a quite decent result. But what many people just tried is just finding an optimal kind of mean prompt. One complication in this competition was that there was no training data, so there was no real proper local cross-validation what one could do. So you had to generate also manually text, which we will talk later about. But this was basically hard to manually optimize, because also you need to try all various kinds of different words in combinations. And in the beginning, what people tried, or also we tried, is to find like coherent text, right? And like this, improve the following text. But what we actually found, which is an artifact, the shortcoming of the metric, however you want to see it, is that actually the meaning of the text does not matter at all, but it is just about finding the good tokens that have a high similarity. So it can be nonsense tokens, as we will see from an understanding point of view, but it will be a good token for generating good embeddings, which is good for the metric. So in our local setup, we actually decided to now, so T5 has, as many other models, has a typical tokenizer with 32,000 tokens. And what we tried locally is to just brute force all these 32,000 tokens to find the most optimal average prompt. So in this case, actually also how this T5 metric usually works is that in the end, it has this end of sentence token. But on Kaggle, and also like if you run it with TensorFlow locally, you cannot actually insert this \s token manually, because it will not be actually encoded as an EOS token. So you have to find ways around it. Actually, if you start this brute force locally, one of the first important tokens is exactly this weird Lucrarea token, which is actually the most similar one to this EOS token. And then just after manually brute forcing this locally to find like, let's say 30 tokens, sequence of 30 tokens that have a good average score, we got to something like 0.65, and probably some other competitors even reached higher scores with just a simple, not simple, but average prompt. Exactly, and here we can see now in this like global solution of us, an average prompt, if you read it, it doesn't make much sense. But yeah, it's like a dot in the beginning, then it's Lucrarea. It really likes this, this weird token. We actually didn't even notice this one is the closest one to EOS. This was discussed in other solutions, but our brute force immediately found it as an important token. So I personally see this a little bit like, let's say, an intercept in a simple regression model. So this is kind of the starting point we started from, and we needed to have this because, yeah, this is, otherwise you cannot get to these high scores, because that's a little bit how the metric works, I would say. But yeah, this was not enough. You could optimize this average prompt more and more, but you needed more. So in this case, of course, we wanted to solve this with different modeling approaches, because that's what we like to do. And the most low-hanging fruit, which we also obviously tried already in the beginning, is to just fine-tune an LLM to try to predict the prompt, right? So you can just do typical LoRa or full fine-tuning of any of the open source models, to give it the input text, give it the output text, and try to predict the actual prompt. But instead of trying to predict the full lengthy prompt, like please rewrite this text, essay, whatever, as a shanty, we only predicted as a shanty, or as a magical potion recipe, or as a funny exchange, and so on. So we we tried to extract the quintessence of the prompt and just try to predict that one, basically. Because this is very supplementary then to this average prompt that we already have, which already encodes very well this like very generic phrases like rewrite this text, for example. And then we just prepend, as we will see on the next slide in a second, this, for example, just predicting this magical potion recipe. And here we fine-tuned a model or two different Mistral 7B models and predicted these parts and prepended it to this average prompt that we already had. So this actually is coherent text, which gives a boost to both local scores and also the final scores. Handing over to Pascal.
Yeah, and what Kaggle usually involves in all the solutions is that you have a diverse blend in the end with lots of different approaches that you try to squeeze together. And yeah, in the first step, Philip already showed how we can squeeze together the fine-tuning of a model together with a mean prompt that we already got by brute forcing. And interestingly, other approaches to solve this, so besides fine-tuning, we also used 8-shot modeling, already complement that quite well. So you can easily boost your cross-validation score and also your leaderboard score by using different approaches. Apparently, they also give a little bit different boosts in kind of these extreme cases. So this was actually one of the early public approaches to have this few-shot attempt here. So you take a pre-trained transformer model. In this case, it was a Mistral 7B model. And then you show this model a few samples, which we have optimized on our cross-validation to resemble, in the end, a good mix of the training data. And then you pre-warm the answer already with some first tokens like improve this. As we saw, it's usually a good starting point to have a prompt here. So our samples always looked prompt plus answer or prompt plus transformed text. And then the prompt usually has a very specific type. So we include the type of the text here. We manually added something like memo, report, text, and always these very similar types of text that were presented in the supplementary data. And then we enriched that with similar to the fine-tuning step with the quintessence of the transformation. So in this case, text shall be transformed to a cooking show, or should be made more poetic, should be turned into a recipe, etc. And all this text that we got then, taking away the improve this because it's not really adding new information, we also concatenated to the final complete string. And as you can see now in the overview, we have our first pre-prompt, which is kind of the rephrase paragraph, also optimized basically together with the mean prompt. Then we have the 8-shot prompting, the fine-tuning steps twice in these, two models from the fine-tuning steps, and the mean prompt. And then going to the last step, which is actually what we thought the most, or the closest solution by the given metric, is directly predicting the embeddings. So while the metric is, the metric is looking for the best matches between the ground truth prompt and some prediction. And this is done on the embedding space because it's calculated on the cosine similarity. So ideally, we thought that we would be predicting the embedding directly. Of course, that wasn't possible because you always have this additional step going through the T5 tokenizer and the T5 model. So we still tried to train a classification model, which exactly outputs these 768 output embeddings from the T5 model. And then we brute forced again, like similar to how we did it with the mean prompt, to exactly reproduce something or a string that is very close in the embedding space to this predicted embedding. So yeah, this is then again a very strange string that's coming out of here. But in the embedding space, it's really yeah, super similar to what we would expect to be the very closest to the original prompt. Funnily, the T5 models are very not very robust to changes in the prompt. So if you have your ideal prompt, which might be a full sentence, and you only change a single word in that, it will already get from a perfect cosine similarity to like 0.8 or something. It will go down drastically. So having this very close match in the cosine similarity space or in the embedding space is or was crucial for our solution.
All right. Yeah. And now speaking about the data, so for both fine-tuning approaches, we had to prepare some data, right? As we were not given the data in this competition. And the most data effort and most data generation effort was given to this embedding model. And we generated over like about 100,000 extra samples for training the models, and also optimizing the hyperparameters. And we use different models, mostly gamma models, for generating this like new original text and rewrite prompts. And we were using these supplementary texts that were provided by Kaggle as few short examples. But also to add some diversity, we like in the final mix we also included like random original text and random rewrite prompts, not using like any few short examples. And for the validation data for all the approaches, we kind of curated a small set of 350 samples. And it was kind of like generated based on the correlation between the local mean prompts and leaderboard. So we had some kind of like history of our submissions. We just like created a correlation score between their local scores on different samples and this leaderboard scores. And we found kind of the best sample that worked for us. And luckily, it had a very good correlation between like our CV and leaderboard. And in the end, our submission was like, this single submission was the best public, best private, and also the best CV submission. So it means that, yeah, we had a pretty good correlation there. And also like the nice feature of the competition was that their public and private were kind of similarish. So there were no kind of huge surprises on private. And fortunately for us, yeah, we finished in the second place. Yeah, that is it for our solution. Thank you. And do you have any questions? All right.
Paul, do you have any question? If not, I have one quick question, maybe.
And in general, I'd open up this to the entire group. If anyone from any other teams has any interesting questions, please do chime in. But yeah, Ashley, go ahead.
Great, thank you. Yeah, so I'm interested in the last slide regarding the data strategy. I wonder, like, you use different models, like mostly Gemma, right? So I'm interested to hear, like, what's your experience of using Gemma comparing to other models in doing this task? Yeah, did you find any advantage of using Gemma or any other models?
Yeah, I think like the main competitor there was GPT-4, and that is why it was like hard to compete with it, right? So GPT-4 was generating like better outputs there. But gamma models were generating the outputs that was closer to these supplementary texts. So it means that, yeah, we kind of like, it was useful for the competition, but yeah, comparing to GPT-4, it was worse, kind of like if you would use it for any other use cases. Yeah, if it answers your question, but yeah, basically there were only like 2 models. So we also tried Mistral. I think it was on par with like Gamma in terms of quality, but as I said, like yeah, Gamma was more useful in terms of like kind of same distribution that was in the supplementary data, and we thought that yeah, maybe it is more useful for this competition.
Great, thank you. Okay, let me see. There's a ping. Okay, no question, but super interesting solution. Oh, please.
Sorry.
Yeah.
First, amazing solution, guys. Really interesting. I just wanted to know more about the decoding that you guys did for the embeddings to the tokens. How did you guys do it? Congratulations, by the way.
Yeah, I mean, we did it the same way as we did it basically for the mean embedding. So we predict an embedding, right? And then we do really a super greedy search, token by token, for a certain amount of tokens to optimize or get an embedding that is closest to the predicted embedding. And yeah, as written here, if we would just use the predicted embedding, we would actually get, I think, quite a higher score on the LB, but we need to take this step back, optimize the string, and yeah, we lose some points on that one. What we saw is, obviously this is super expensive in terms of runtime. So what we saw is that actually if we initialize it already with kind of the mean prompt we had, we can predict fewer tokens in the end and save some runtime. But yeah, it's really greedy. We limit the space to a certain amount of tokens. So we don't try for all 32,000 tokens, but we do one iteration, like what are the top 1,000 starting ones, and then we just pick, let's say 20, 30 from these potential 1,000 ones. We tried various things with beam search, with like optimizing it further. But yeah, just this greedy hill climb like approach was best.
Amazing, thank you.
I mean, ideally, you would even have a string which then changes also the order of the tokens. So not going greedy, first token, second token, third token, but rather you want to have the, let's say, optimized set of 30 tokens in any order. But that would be a compute requirement that probably the whole universe doesn't have. So here, having this very simple approach of just going one token by another already gave quite good results and was easily being fitted in the Kaggle kernel. We also made our Kaggle inference kernel public. So if you want to have a look there, how exactly it's done, please check it out.
Amazing. It was a great insight. Thanks a lot.
And we also sampled like only, I guess, 20 or 30 tokens in the end, right? But the more tokens you sample, the better, like the closer you get in the vector and the metric grows, right? But yeah, we were limited just by the runtime. And like for our last submissions, yeah, I think it was like very close to 9 hours, right? So we were counting minutes, even seconds for these last submissions.
Yeah, and if you could hard code this end of sentence token directly to the string, you would also have a big benefit on the metric. That's actually how we found it out, because locally I was going through like, how is the T5 encoding, and then there's always the end of sentence token. So just having the end of sentence token should be better than any other single token. But yeah, then we saw LB score is very low, and then we figured out that it is. It's basically exactly what we try to do. It's trying to prevent the injection of special tokens. So but funnily, there is a token that is very similar, which is this Locaria, which is funny inside of this competition, actually.